Hey everyone, and welcome to The Explainer. Today, we're going to completely conquer Chapter 2 of your Class 12 physics syllabus by treating electric potential kind of like a giant topographical map. Seriously, if you've ever looked up at a huge mountain and wondered just how much energy it would take to hike all the way to the top, well, you're actually already halfway to understanding electrostatics.
Okay, so let's jump right into this. Think about what it actually takes to move and store electrical energy. We know that every time a charge moves through space, it's either doing work or work is being done on it. But what happens when you trap that energy? Like, how do you practically bottle lightning?
Well, to answer that, we're going to follow the journey of the charge. Today we'll be covering the power of potential, mapping equipotential surfaces, capacitors, the great dielectric dilemma, and we'll wrap up with some classic exam traps and tricks.
All right, let's kick things off with Section 1, the power of potential.
It's actually crazy how much electrostatic potential mirrors gravitational potential. They're both conservative forces. That means the actual work you do hiking a charge up an electrical hill depends entirely on where you start and where you finish, not on whatever winding, crazy path you take to get there. But you definitely can't forget the one massive difference. Gravity only ever pulls, right? But electrostatic forces can actually push back. So, at the end of the day, electric potential, which we just call V, is really just measuring the potential energy per unit charge at a specific spot. Think of it literally like measuring the altitude on our map. You're doing work, W, against the electric field to drag a test charge, Q, all the way from infinity to a certain point. Do 1 joule of work for every coulomb of charge, and boom, you get 1 volt. And because V is inversely proportional to the distance r, that potential naturally drops off as you move further away. It starts as this really steep hill right near the charge, but as you move outward, the slope just gradually flattens out towards zero.
Now throw a dipole into the mix, a positive and negative charge sitting a tiny bit apart, and things get a bit more interesting. The formula now depends on the angle, theta. And guys, here is a classic exam trap to watch out for. If you place a point directly on the equatorial line of a dipole, the angle is exactly 90 degrees. And since the cosine of 90 is 0, the potential right there is just 0. It's basically a perfectly flat valley right between the two charges.
Moving right along to Section 2, mapping equipotential surfaces.
See those dashed lines forming those really cool symmetric patterns? Those are our flatlands. We call them equipotential surfaces. Because every single point on one of those lines has the exact same potential, it means absolutely zero work is required to move a charge along that surface. You're literally just walking along a perfectly flat ridge, never going up, never going down.
But what happens if you step off that ridge? Well, that brings us to a huge rule, represented by the formula E equals negative dV over dr. This is the negative gradient relation. It essentially tells us that the electric field, E, always points straight down the absolute steepest part of the potential hill. And naturally, the closer those flat ridges are to each other, the steeper the drop-off, which means a much stronger electric field. Graphically, this is super straightforward. The electric field is quite literally just the negative slope of your potential versus distance graph. So if you're ever staring at an exam graph and you see a flat, zero-slope region for the potential, you instantly know the electric field right there is 0. It's simple. No slope, no field. All right, Section 3, capacitors, and how we actually store all this energy.
Okay, let's talk about capacitance. If we're using our landscape analogy, a capacitor is basically an energy dam. It's defined as the charge stored per unit of potential difference, so C equals Q divided by V. But take a close look at that second formula for a parallel plate capacitor. This tells us that capacitance is entirely about physical geometry. Make the plates bigger, increase A, or push them closer together, decrease D, and you instantly get a larger capacity to store charge.
Now, when you're wiring these dams together in a circuit, you've got to pay attention because it's the exact opposite of how resistors work. Putting capacitors in parallel gives you more total storage area, so you literally just add their values together. But put them in series, and you actually decrease your overall capacitance. And no matter how you wire them up, the total energy trapped inside that field is always U equals 1/2 C times V squared.
Next up, Section 4, the great dielectric dilemma.
Guys, I'm not kidding. This right here is an absolute cheat code for your exams. Take a mental screenshot of this.
Whenever you slide an insulating material, a dielectric with a constant K, between the plates, the capacitance is always going to increase, no matter what. But everything else, that depends entirely on the battery. If it stays connected, the battery forces the voltage to stay constant, so the charge has to increase. But if you yank that battery out first, the charge is trapped. It stays constant, which means your voltage and electric field drop.
Finally, let's wrap up with Section 5, Exam Traps and Tricks. Let's look at an actual NCERT exemplar problem where they really try to mess with you. They set up a capacitor with a dielectric, disconnect the battery, and then ask what happens when you pull the dielectric out. It's the total reverse of the normal setup. So, breaking down the logic here, since the battery is disconnected, the current has literally nowhere to go. That's your anchor point. The charge, Q, is totally stuck. It's fixed. When you pull the dielectric out, your capacitance obviously drops. And since Q is constant, but C just dropped, the voltage across those plates has to suddenly spike. And because of that, the total energy stored, U, also shoots up by a factor of K.
But wait, hang on a second. Energy has to be conserved, right? If the battery isn't even connected to pump energy into the system, where in the world did this sudden spike in stored energy come from? Well, this perfectly shows the real-world physics of work. The dielectric is naturally drawn inward by the capacitor's electric field, so to get it out, you have to physically pull it. The mechanical work your muscles do to yank it out is literally transferred straight into the electric field, becoming that extra stored potential energy. How cool is that? And that wraps up our topographical tour of Chapter 2. Look, if you can actually visualize this stuff, seeing how a charge moves across this landscape, feeling those steep slopes of the electric field, and seeing capacitors as energy dams, you won't just be memorizing dry formulas, you'll actually understand the core logic of electrostatics. So, with this new map in hand, what other invisible fields are you going to map out next? Keep exploring, keep asking questions, and I'll see you in the next explainer.